Okay, so before we talk about the details of some sample hash functions, because I know it's probably hard to imagine how these things work, I forgot I want to talk a little bit about what the strategies are when we have conflicts. In other words, when two objects hash to the same value. I mentioned chaining and linked lists, but I want to talk a little more generally about that first. Let me share my screen and continue with the notes. So talking about the hash function, I know it's a bit of a mystery how we can come up with this magic function, but remember in general we can't. Okay, there is no such magic function. In a few specific cases where all the possible values are known in advance, which is not typical. Again, typically we're getting things like customer records and we don't know who it's going to represent. But there have been cases where it's been possible to compute a perfect hash with no conflicts. And again, order m equals order n memory. That's important. But what's the next best thing? Well, the perfect hash function tells us exactly where to look, but in general, we just want a hash function that tells us where to start looking, and we want that looking process to be somehow bounded as the number of elements that we are storing increases. Okay, so that's the idea I told you, but let's just look in practice of how this would work. So again, very simple example. We want to hash fruits, but now honeydew hashes to 6, which is a conflict with mango. So you see we have mango in slot 6. And what do? We already have something sitting in the underlying hash table. Well, I told you we could build a list, but let me just talk more generally about what we might do when we have these things called collisions. Okay, so when two values hash to the same array location, it's a collision, and collisions can be treated in different ways. What do if we do first come first serve? Someone's there already. What happens to subsequent values? So solution one is we can search for a nearby empty location. Okay, so we can say, all right, honeydew hash to the same place mango did, but is there an open slot in the hash table that hasn't been used yet? And can I maybe step my way to that location in such a way that I can find it when I need to look it up? Okay, and that would require an end around search. So when you got to the end of the list, you would have to be able to wrap around to the beginning. Second solution is to use a second hash function and a third and a fourth. So, and they would be different. So you would hash, say, honeydew, get the same thing as mango, and then you would hash again with a second hash function, and that would give you a second place to look. So that turns out to be a pretty uncommon approach, but you can do it. And I'll give you a little more examples when I talk about it. It's called rehashing. And the third possibility is the one I mentioned. It's called a chained hash table, which is to use the array location as the header of a linked list of values to the hash location. Okay. And they all work provided that we use the same technique to add things to the array as we use to look things up to the array. There will be some limitations on the probing the so-called open hash table, which is solution number one. But we're really interested. I strongly recommend just doing number three, but it's good to see what's out there. And there is some diversity in the things people use. So it's important to be aware of them. Suppose we want to add this underlying hash table Boston to a list. Okay. And you see that cities have hashed index values. You have no conflicts yet. And imagine though that Boston hashes to the same thing as Austin. Okay. So you hash it, you get 143 is the index for insertion. You see it's taken, then you go down the list. Table 144 is not empty, so you don't put Boston there, but table 145 is, so you put Boston in 145. Okay, so you just look for a nearby location. That way you don't have to create these lists that cost extra money extra memory, and you use what you have already in the underlying hash table memory layout. So we slide Boston in there. Now say we want to look up Boston in the hash table. It's the same thing. Suppose that hash code Boston is 143 and you look there and you do a test and you find out it is not Boston. In fact, it's Austin. So you advance to 144, same thing, 145, and you find Boston. So you're able to find what you, where you originally stored it, okay, at location 145. Now I think you probably see some shortcomings with this, but depending on what you want to do. Let's take another example. Suppose you want to look up Portland in the hash table, okay? And also suppose that Portland hashes to 144. Okay, so table 144 is not empty, but it's also not equal to Portland. 145 is not empty, it's not equal. Is empty, and if Portland were in the table, we should have found it by now, right? Because it would be location. Therefore, Portland is not there. Okay, so now suppose you want to add Miami to the hash table, and also suppose that Miami hashes to 143. Well, 143 is not empty. 144 is not empty. I'm sorry. 143. I got myself confused for a second. Table 143 is not empty. Table 143 is not equal to Miami either. Table 144 is not empty. Table 144 is Miami. So Miami's already in the table, so do nothing. Okay. Now say you want to add Seattle to the hash table. Seattle hashes to 147. The last location is 148. 147 and 148 are occupied. So like I said, we treat the list as circular and we come around to 0, and hence Seattle goes in 0, or if it's taken 1 and 2 and so forth. Okay, so there's some problems with that technique. One problem just in practice is that it tends to form clusters because you're always searching nearby locations. And so you'll have little areas where you have lots of keys, you have lots of other group of keys and big maps. Okay, so you end up having to probe pretty far. The bigger a cluster gets, the more likely it is that new values hash to that cluster and make it even bigger. And so they cause efficiency to degrade. So there are other ways, other modifications people have made to this. Instead of stepping ahead one step, for example, step n locations ahead. Okay, well, I call it a non-solution because the clusters are really still there. You just can't see them visually because they're not next to each other in index space. So unless the n and the table size are mutually prime, some table locations will also never be checked. Okay, so you'll be skipping parts of the table if you do that. So it turns out that the clustering makes it not the most efficient approach. Before I say anything about efficiency, let me mention the obvious thing, which I did say, which is deletion really complicates this for open hash tables. So you can't simply delete it, just say it's available for reuse. If you want to delete a key, you have to mark the keys in different ways, and becomes a little bit intricate. I forget the exact details of it. And then people have proposed more clever ways of doing deletion, but it's not straightforward. Okay, and I'm not going to get into it just because I don't think that type of hash table for any applications I've used is any better than doing a chained hash table, but I just wanted to make you aware of what it was. Let's talk a little about efficiency. Hash tables are incredibly efficient if they're done remotely well. So until the table's about 70% full, you typically only have 2 or 3 probes if you're using this open address hashing. Takes a lot of sophisticated analysis to prove that the expected cost of inserting into a hash table is order 1. Even if the table is nearly full, efficiency is still quite high. Okay, so let's talk about solution 2, rehashing. In the event of a collision, another approach I said is to compute another hash function. And we might need to do that a 3rd time and a 4th time and a 5th time. So a simple example, if we're thinking about hashing strings, we could take the first hash code and we could add extra information to it to get a second hash, like the length of the string. Or maybe if the length of the string was not a component in computing the original hash function, that would work better. But if it was, you would maybe choose something else. Okay, and it's an art form, no question. Better yet, maybe add the length of the string plus the number of probes made so far. But you have to keep a record of the sequence of hash functions that you use, which is easy. You just store pointers to functions in a table. One problem is, are we sure that we will look at every location in the array? So when you compute a sequence of hash functions, if you're not very careful about it, you could skip all over the underlying array. And that's similar to the problem of clustering, or at least the problem of not getting full coverage when you're doing the open address hash table. Okay, so rehashing also sort of fell out of favor. These are things that were popular different periods and people worked on them, and they kind of come and go. But I still think now, at least in my own personal experience, chained hash tables are still overall a better choice, except for particular applications. So let's talk about what I call chained hash tables, which I'm calling here bucket hashing. There are different names for it. But in that case, we're going to use, like I said, linked lists to handle collisions. So the previous solutions used open hashing in the sense that you just try to find another spot in the underlying data structure if the first place didn't work. Another solution is to make each location the header of a linked list, right? So if you hash Portland and it has a conflict and Seattle's there, rather than looking around at the table, just add Portland. Normally you would put, depending on how the list is drawn here, you insert it at the head of the list typically, because that's a constant time operation. So we're going to talk about, or we will during the lecture talk about a C implementation of a chained hash table. And it's a nice sort of combination of new things and things we've done so far. And the code is very short when you put it all together. So I want to now talk about computing the hash function. And I want to do it by breaking up the computation of the hash function into kind of two pieces. Okay, and I'll do that in the next segment to keep the segment short. But the idea will be that if we have an arbitrary object, sort of step one in hashing will be to turn that object into an integer value. And step two will be to turn that integer value into an integer value that fits into our table. And of course, not just fits into it, but that spreads out in some sense nicely over the table. And there are many more ways to do the first part than the second part. And a lot of books don't break the two steps, break this up into two separate steps, but for analysis purposes, it turns out to be very useful.